Chapter 7, Rhythm of Life, from the book Nature's Number by Ian Stewart.
Hello, I'm Kriztina Zea J. Bitun.
I am Lyka I'm Lerona.
Amie, Nicole, Encarguez.
And I am Abigail, Sacayle.
This time, our group will be talking about Rhythm of Life by Ian Stewart.
We live in a universe of repeated pattern. Animals in the savanna, like zebra and cheetah, are covered in pattern spots and many more animals. Every night, the stars above us are twinkling and moving in circles across the skies. And also, humans' heart and lungs follow rhythmic cycle. Indeed, as Muybridge founded, mathematics is both an art and science. This chapter is composed of 4 major points: the gait analysis, the oscillation concept, the Hopf bifurcation, and the symmetry breaking theory. To further explain these major points, let us proceed to the first point or concept, which is...
The first point or concept of this 7th chapter is gait analysis. So what is gait analysis? It is a branch of mathematical biology that grew up around questions: how do animals move, and why do they move like that? It started with Edward Muybridge, but first, who is he?
Edward Muybridge, born as Edward James Muggeridge on April 9, 1830, and died May 8, 1904. He was an English photographer known for his pioneering work in photographic studies of motion and early work in motion picture projection. He adapted a mechanical device known as zoetrope to display them as moving pictures.
Muybridge photographed a detailed sequence of 4 scallops. This shows or tells that mathematics helps us understand this concept of locomotion not only in the movements of animals but also in people. It can be applied on many different levels and to many different things.
Nature respects unity and makes good use of it.
The next point or concept is the oscillation concept. Oscillation is the organizing principle behind many such as biological cycles is the mathematical concept of an oscillator. A unit whose natural dynamic causes it to repeat the same cycle of behavior over and over again. Or for short, oscillation is to move back and forth in any regular rhythm. Have you noticed why a tiger cannot sit still in his cage? That is because of the combination of the 2 constraints. Oscillation cannot only be observed in the movement of animals, but also in any action done by a human that shows a repeated motion. Even our daily routine can be considered as oscillation because we repeat same action every day.
This time, let us proceed to the third concept, which is the Hopf bifurcation. In 1942, the German mathematician Eberhard Hopf found a general mathematical condition that guarantees such behavior. Hopf proved that if the simplified system wobbles, then so does the original system. The word bifurcation is used because of a particular mental image of what is happening, in which the periodic oscillations grow out from. An example of this is the clarinet. When the clarinet was blown slowly, it creates a good and soft sound. On the other hand, if it was blown loudly, it will produce a bigger sound. This is typical of Hopf bifurcation. If the simplified system passes Hopf mathematical test, then the real system will begin to oscillate of its own accord.
We are now on the 4th major concept of the chapter 7, the symmetry breaking theory. The symmetry breaking theory also explains how animals can change gait without having a gearbox. A single network of oscillators can adopt different patterns under different conditions. The possible transitions between gaits are also organized by symmetry. Did you know, the faster the animal moves, the less symmetry its gaits has? More speed breaks more symmetry. As an example, an elephant that has only one gait of rhythmic pattern for moving their limbs, they can only walk. But when it wants to move faster, it ambles. And when they move their leg, the patterns are the same. The big message in both locomotion and synchronization is that nature's rhythms are often linked to symmetry, and that the patterns that occur can be classified mathematically by invoking the general principles of the symmetry breaking. The principles of symmetry breaking do not answer every question about the natural world.
The lesser message is that mathematics can illuminate many aspects of nature that we do not normally think of as a rhythm of life being mathematical. As what being said a while ago, we live in a universe of pattern. Everything around us is organized in rhythm. Indeed, mathematics in nature produces the rhythm of life, and surely mathematics helps us understand and appreciate the world. And in exchange, we use the world and its wonders to understand and appreciate mathematics.
And that's it! We hope that you learned something on the chapter 7 of the book Natures of Numbers by Ian Stewart, The Rhythm of Life.